Hi class, welcome back. Today we're going to discuss the extrema on an interval. The objectives are to understand the definition of extrema of a function on a specific interval, understand the definition of relative extrema of a function on an open interval, and then make a conclusion on how to find an extrema on a closed interval. So we'll begin by defining an extrema of a function. So it's important for us in calculus to devote some time and determine the behavior of a function on a specific interval. Now, I remind you guys, what does it mean to be an interval? So if we're talking about an interval of a function, we're referring to usually in terms of x. So if x is between two numbers in the number line, so that will be described as x is between a and b. Now, because there's no inequality, there's no equal there, that means that x is strictly greater than a and strictly less than b. So therefore, we can describe this in this interval with parentheses. Or we can say that x is between a and b, but x can be a and x can be b. And in that case, we'll put brackets. Or we can say that it is halfway, right? We can say that x is strictly greater than a, but x is less than or equal to b. So that way we're going to have parentheses in the bracket, right? So what we're saying here is that there's a function, and we're trying to define the behavior of a function between an interval of x, right? Now, what kind of behavior are we going to we're going to talk about in this section? In particular, we're going to talk about the behavior of having a maximum value of f in this interval. Do we have a minimum value? Where does the function increase and where does the function decrease? That kind of behavior is what we're interested. And in this section, we're just going to particularly focus on the maximum and the minimum. We'll discuss those the other ones after these sections. So let's first let's look at this picture, right? So when we talk about the maximum value of a function, remember that f of x is the y component. So obviously, if your function has here's your function right here. If your function has a high point, that means that that's greater than any point on the bottom part, right? Any point on the bottom part. So in this example, f of x has a maximum value, right? It's the most that it can get to, and in this case, the most it can be is 5. Now we look this into the number line. We can see that the highest point that it reaches, right? It'll be f of 2, which happens at 2. F of 2, because the value of the function is 5. So here's your x, here's your y. Now, when we refer to maximum, we're referring to the y value. So this is the maximum. And what does the 2 mean in this example? Well, 2 is the location where you can find the maximum. So x is going to be used as the location, as a reference of where you can find this particular maximum value. Now, just like in this example, you have a maximum, but if you guys notice, the numbers are getting smaller for the value of the function. In other words, the value of y, to the point that it reaches its lowest point on the graph. The lowest point in the graph, which happens to be y equals 1. So at y equals 1, happens at x equals 0, but this minimum point of y is 1. 1 is the minimum point. Now, if you guys notice, a minimum point can be a positive number. Just like we're going to see, sometimes a maximum point can be a negative number. So just keep that in mind, what I just said. So how are we going to define this? Well, if you notice, this point was the smallest, the lowest point of the entire graph, and this point was the highest point on the entire graph. So does every function have a maximum? Does every function have a minimum? Well, we're going to answer that question in this section. And if so, if it does have a maximum, it does have a minimum, how can we find it? Well, let's see over here. Does this function have a maximum and minimum, right? So we're going to ask that question. Well, what happens here is that as this function is trying to find the highest point on the graph, we see that highest point on the graph is not defined. The function is not defined where it would be the highest point in the graph. So therefore, in this example, there is no maximum point. Because if you guys think about this, what is happening in the behavior of this function is that the function is getting bigger and bigger and bigger and bigger as x is getting closer and closer to 2. But you're never going to get to 2, right? You're never going to get to 2 because if you notice, x is described in an open interval where 2 cannot be reached. So therefore, you're never going to be able to get that number 5. So therefore, we can say that if there is an open circle on the graph, there is no maximum value here. Now, what happens for the minimum value? As we're trying to find the lowest point on the graph, we can see here that, hey, we are just like the previous example, we do have a minimum value, and it happens at 0, and the minimum value is y equals 1. So there is a minimum value. Now what happens over here? Well, we can see here clearly that this is not going to be a maximum because we know there's points higher than that. All right, let's think about the other one over here. Do we have a maximum? Do we have a minimum? Right? So let's look at the maximum. So just like in the first example, we do have a maximum because we do reach that point, and it is the highest point of the function, right? So in order to be a maximum value, it needs to be a y value on the function. It must be defined. So that's defined, but this is not defined. That's one way you can kind of think about it. Let's find the minimum value. So the lowest point on the graph, as we go down, we can see that it would have been here, but we have a hole. That means the function is not defined. I mean, actually not defined here, but it's actually defined there. So there is no minimum because there's no minimum value. The value does not exist there. It's not defined in here. So there is no minimum value. Again, we would have to have an actual hole to be able to have a minimum value. Now, we can see here that it's very easy for us to find a maximum and minimum by looking at the graph if the graph is labeled. But the question that we want to ask ourselves, and that's where we're going to derive most of the energy for this section, is if I just give you this function and I just give you the interval, would you be able to determine the maximum and the minimum of the function? Let me say that again. If I don't give you the picture and I just give you the actual function and the interval, would you be able to determine the minimum and the maximum of the function? Right? That's the question we want to ask. Now it's very easy right here because we can see it. So we're going to have to explore that direction, right? So let me go back to the definition now that we have sort of a better sense of what we're talking about with minimum and maximum. And this way we can kind of look at the details of a definition. So we have a function f that is defined on some interval I. It's very common for us to define intervals as I. Just interval, this means like something of this form. Containing an x value of c. Right? There's an x value of c inside this interval. F of c, the y value, is the minimum, right, of f on that interval whenever f of c is the lowest point of all values of the function for every x value on I. Meaning that if x represents every number in I, and you define and you find that value in the function, those numbers for x will always be bigger, will be always higher than this number. In a similar way, we can argue the same thing for maximum. F of c is the maximum value of f on the interval I when f of c is the greatest or equal to a number, to a function value for all the values of x in I. So every number of x in I will always be smaller or equal to f of c. So that means that f of c is the maximum of all, right? All right. So let's define some definitions here. Now you do have to be familiar with these definitions, and we're going to be doing this so often that you guys will get used to it. So let's see. The minimum and maximum of a function on an interval are the extreme values, or extrema. The singular form of extrema is extremum. If you guys think about the word extreme, it's like the most, right? The most. So we can think about extrema as the biggest point, the maximum point, that there's nothing else beyond that, right? So extrema values of the function on the interval. The minimum and maximum of a function on an interval are also called absolute minimum or absolute minimum. So we can also refer them as absolute minimum and absolute maximum. Absolute, right? There's nothing beyond that. Or we consider them as global minimum or global maximum on an interval. So those are terms that we use for absolute max, absolute min. Now, I will refer them as most of the time as absolute max, absolute min. Once in a while, you will also see them as extreme. Global is not as common, but that's another way we can also refer them. Extrema can happen in the interior points or the endpoints on an interval, as we see here, right? We see in the picture. We notice that the maximum of the function happen at an endpoint, right? But also we can see that these extremas can also happen in the interior of the interval, right? Within the -1 and 2. So what we're saying is that you can find these maximums and minimums in either the interior of the interval or the endpoints of the interval, as we've seen in this previous example. Let's see. Extrema that happens at endpoints are called endpoint extrema. All right, so we already talked about this example. So now let's ask this question: Is there like a function, or what does the function, or what are the requirements needed? What requirements are needed in order for us to guarantee that there is a extrema value in the function? Meaning, what conditions do we need in order for us to have a minimum and a maximum on the interval? Well, if you guys notice, this first example does have maximum and minimum, but this one didn't have both of them, right? So what made it not have a maximum in this example? Well, the fact that the endpoint was not included. So maybe we should start with having the endpoints included in the interval, meaning like this, having them brackets. So the function needs to have the interval that we're describing, the function must be closed, meaning that it has to have both endpoints. What about the other one? What happened? What was wrong with this one? Well, in the interior part, there was a point missing. So what about, how can we fix this? Well, we require the function to be continuous. So there you go. So if we make the function continuous on a closed interval, then we're guaranteed to have a maximum and we're guaranteed to have a minimum. So let's look at this. If f is continuous on a closed interval a to b, then f has to have a minimum and it has to have a maximum on that interval. I hope that kind of makes sense, right? So that's sort of like the theorem that we're going to be using, but we can see in the picture why those are required. All right, so those are the extreme value, minimum and maximum. There are also other types of extrema, and those are called relative extrema. So let's see this picture first. Now, in this picture, we have a function that is here described in black, and it keeps going forever, right? There's an arrow that means that this is going to go forever, this is going to go forever. Now, a relative max, well, we know what's a max, but what does it mean to be relative? Well, relative is referred to relative to its surrounding. That there is a maximum value relative to its immediate surrounding. And when we define this surrounding, it's a surrounding, it's an interval that is an open interval, right? We don't need this to be closed in order for us to have a relative extrema. So if we notice, it will happen if we restrict the graph. If we restrict the graph between here and here, then we can see here that the graph will only exist for this part, right? Like we only have this part right here. So let's see, we're only gonna have let me put this in red. So we only have this part right here, right? So but nonetheless, in this open place, we will have a max, right? Well, this is referred to as a relative maximum. In a similar argument, we can say that if we restrict the graph between around 2 with open intervals, so we can see that if we restrict that, right, then we can kind of see that there will be a relative min, right? Those are open. We're gonna have a relative min. So if you guys notice, we don't have to think too hard here because we can kind of make sense of by looking at the pattern. So what we're saying here is that we will have a relative max and relative min whenever this happens, whenever there is this change, or whenever there is this change right here. But if you guys think about it, this picture, this description sort of looks like a hill. If you pass through a hill, then that means you have passed through a relative max. If you pass through a little valley, right, if you think about this valley right here as a valley, then you have passed through a relative min. And that's how we actually see it in that's how we actually think about it in our minds, right? I see a little hill, that's a relative max. If I see a little valley, then that's a relative min. All right. So in this example, this function has a relative max and a relative min, where there is a relative max at 0 and the relative max is 0. There's a relative min at 2 and the relative min is -4. Now when we refer to relative max and relative min, we often also refer to them as points. F has a relative maximum at the point 0, 0. F has a relative minimum at 2, -4. Now what is interesting for us to note here is that this hill is sort of kind of interesting, because if we think about the relative, where the relative max is at, there is sort of like, if we draw a tangent line through that point, because every point has a tangent line, we can see that that this is a tangent line, and this tangent line has a slope of 0. With a similar argument, we can say that this relative min also has a slope of 0, right? So these two, so what this is suggesting is that we can sort of make a connection between relative max and relative min to having a slope of 0, right? And we're going to discuss this further here. So now that we have discussed this, let's talk about the definition. Let's see. So if we have if there is an open interval containing C, let me maybe draw a picture here, containing C, on which f of C is the maximum, then f of C is called the relative maximum of f. Or you can say that f has a relative maximum at C of C. So you can say it two different ways, right? We should recognize that the relative maximum is f of C, but you can find a relative maximum at C f of C, right? So that's the language we're gonna use. That's how we're gonna interpret this type of language. In a similar argument, we can say if there is an open interval containing C, here's your open interval, containing C, here C is 2, then f of 2 is the minimum, and f of 2 will be called the relative min of f. Or you can say that f has a relative minimum at C of C. So the plural relative maximum is relative maxima, and the plural of relative minimum is relative minima. Relative maximum and relative minimum are sometimes refers as local max and local min. If you guys think about this, it is sort of like the maximum relative to its immediate surrounding, but you can think about it as it is the local max because it is the maximum referred to its local area, right? around this neighborhood. So now let's think about this, because in this example we can see here that there is also, let's explore this concept here. We also see here that there is a relative max here. Notice here that this is, by definition, the highest point in its immediate surrounding, right? Just like over here, we can see that this is a relative min. By definition, it is the lowest point in its immediate surrounding. There's nothing lower than that. So, but what we have here is that this gives us a different approach. A different alternative. We can see here that in this example, the slope of this is undefined because there is so many slopes, tangent lines we can put here. So here the slope is undefined, and here is also undefined. So what I'm trying to say here is we're trying to explore all the cases that we can get. So we can say here that when the hill or valley is smooth and rounded, the graph has a horizontal tangent line at a high point or low point. But also when the hill or valley is sharp or peaked, the graph represents a function that is not differentiable at a high point of that. So both cases, when the slope is 0 or when the slope is undefined, will give us either a relative max or relative min. Now, does it always going to give us that? Would that give us always that case? We'll discuss that in a second. So in the next example, find the value of the derivative at each relative extremum. So example 1, the relative max of this picture right here of A. If you notice, the graph is increasing, and then it goes horizontal, and then it starts decreasing. Well, here where the tangent line is horizontal, that means that this will give you a relative max or min, in this case relative max. So we see that there is a relative max at 3, and the relative max is 2. What about this one? Well, here we see a sharp corner, right? We can identify the sharp corner, and we say, okay, this is a sharp corner, then this will be a relative min because that's the lowest point in its immediate surrounding. And in this case, the derivative does not exist there, right? The derivative here is 0. Here we have both relative max and a relative min, right? Here's a hill, here's a valley, and we can see that in both cases the derivative is 0. So that gives us that sort of conclusion, right? We can sort of be able to find these critical numbers very quickly by looking at the picture. This relative max, relative min by looking at the picture. So note in example 1 that each relative extrema, the derivative either is 0 or does not exist. So the x values of these are special points called critical numbers. So we're going to call this whenever this happens, whenever you have a change, whenever you have a peak, right, or wherever you have a derivative be undefined, or wherever you have your derivative be 0, then we're going to call those critical numbers. So we're going to call those critical numbers when those two happen. So let's see this picture here. So here the derivative is undefined, does not exist. So here is a critical number at C. Here's another critical number at C because the derivative at C is 0. Here's another critical number because in this case the derivative at this point is 0 as well. So then we're going to define the critical number of f is defined at C if the derivative at C is 0, or if f is not differentiable at C, then we say C is a critical number. So those two will help you find the critical numbers, right? Whenever this is true and whenever this is true. Now the question is, the next question is that C must be part of the domain, right? We want to make that clear assumption that C must be part of the domain of the function, right? F is defined as C, so C is part of the domain. So notice the definition above that the critical number C has to be part of the domain of F, but if C was not part of the domain of F, then C does not have but in that case, then C will not be a critical number, right? A critical number needs to be part of the domain of F. Now, C does not have to be in the domain of F prime, right? It has to be part of C, domain of C of F, but not in the domain of F prime. Let me say that again. C needs to be part of the domain of the original function, but C does not have to be part of the domain of the derivative function, as we can see here, right? Because this implies if F is not differentiable at C, that means that C is not part of the domain of F prime. All right, so the next question that we have, or the next theorem, is very important. If F has a relative minimum or a relative maximum at C, then C is a critical number of F. So what we're saying here is that if we know that we have a relative max, then either we can say that F prime does not exist, or F prime is equal to 0, right? Because in both cases here we have a relative max. So we are guaranteed to either have F prime does not exist or F prime is equal to 0. So that sort of kind of makes sense, right? That if F is if you already know that F has a minimum or relative max at C, then you can conclude that C is a critical number. Remember, critical number is referred to, sorry, let me jump in over here. Critical number is a C value that will give you a derivative of 0 or F be differentiable at C. But my question that you guys want to ask, and I want you guys to pause that and make sure you guys are familiar with these two, the definition of the theorem. But I want you guys to now think about the next statement. Is it true or false? Reverse statement of this, the reverse statement of this. That is, if C is a critical number, if I work backwards, if C is a critical number of F, then F has a relative minimum or relative max at C. So if you already know that you have a critical number at C, does that imply that it is a relative max or relative min? And the answer is no. That's a false statement. And we can see it here. Because here, we can clearly see that this is a critical number at C. But if you guys notice, in this example, this is not a relative max. Because in relative max, you must be a hill. And this is not relative min because this has to be a valley. So it is neither a hill or a valley. So therefore, this is not a relative max or relative min. So be careful with this statement. This statement only goes one direction, right? F has to be a relative min or relative max, then then C is a critical number. But if C is a critical number, that does not guarantee to be a relative max or relative min. All right, so we do have now. If you notice here, we sort of have we can now find this these points, right? We can now find these points right here. We can find that point, or this point on the graph, right? We can find where there's a relative max or possible relative max or possible relative min. If you think about it, that's sort of giving us opportunity to find this. So we already know that we can find this, and by this theorem, it says that we are guaranteed to have a minimum or max, and we already decided that your absolute max or your extrema, your minimum and max, will happen in the interior or in the endpoints. So we can find the interior where you have a relative min or relative max, and we can also compare it to the endpoints. So what we're saying here is this conclusion that's very important. Theorem 3.2 states that relative extrema of a function can happen only at critical numbers of the function. Knowing this, you can use the following guidelines to find the extrema on a closed interval. So if you need to find the extrema on a continuous function that is closed interval, then we can find this by using the following steps. Step number 1, find the critical numbers of f in the interior interval of a and b. Then evaluate f at each critical number, a and b. Then do the same thing for the endpoints. Now evaluate f at each point of the endpoints, and then compare. The least of these values will be the minimum, and the greatest of these values will be the maximum. So this strategy is very, very common for us to do. So let's find the extrema on the closed interval. Find the extrema of f of x. So here we have a function. First of all, we should check, is this function continuous? Absolutely, right? We know that we have to check that part. So f of x is continuous because f of x is a polynomial. Now, are we defining this f of x on a closed interval? And that is correct. So we have checked this part and we have checked that part. So we are not going to have a problem like over here where the endpoints are not there, or whenever you have a hole in the interior. So we already removed, we already know that those will not happen in this example. So we are sort of guaranteed to have them, right? To have this extrema. Alright, so first it says find the critical numbers within -1 and 2. So find the critical numbers, and we know that we can find the critical numbers by finding the derivative and finding where the derivative is 0 and where the derivative is undefined. So we're gonna sort of break this into two cases. So let's find when the derivative is 0. So set it equal to 0. So I will set this equal to 0, and then find the value of x where this will be true. So find the x value. If you find the x value, you have found the location of this critical number. So you'll find this critical number. So let's set this equal to 0. And so for x, we notice that the both terms have a 12 and x squared as a common factor. So we're going to factor that out. We're left with x minus 1 inside the parentheses. So that product is equal to 0. By the 0 factor property, this suggests that this needs to be 0 or this needs to be 0, right? If this is 0, right, then the only way this will be 0 is whenever x is 1, right? So that will be that part. You can do this by actually doing it by writing it. X minus 1 is equal to 0. Add 1, x equals 1. What about this one? 12x squared equals 0. Divide both sides by 12. So you set them equal to 0. Kind of what we did in algebra, right? And we take the square root of that. Plus or minus square root of 0 is 0. So we found out that x equals 0 and x equals 1 are critical numbers. And what are we going to do next? It says here to plug in to evaluate the function at those using those two critical numbers. So plug in x equals 0 into the function, into the original function, which is over here. So we plug in 0. Using f of x equals 3x to the 4 minus 4x cubed, right? Plug in 0 here, plug in 0 there, and plug in 0 there will give us 0. Plug in 1 there, plug in 1 there, plug in 1 there, that will give us negative 1. So that was second part. Now third part is to go ahead and evaluate the function using the endpoints. So look at the endpoints of the interval, -1 and 2. Plug in -1 into the original function. -1, -1 will give us 7. Plug in +2, that will give us 16. So now at this point, you're going to look at the values of y. You have a 0, you have a -1, you have a 7, you have a 16. So obviously the lowest point of the function is going to be -1. So the least value of f is -1, and we can see that it happens at x equals 1. The greatest value of f is 16, and it happens at x equals 2. And we can see that here, the picture to kind of confirm that. We see here that at 1 we have the lowest point, and at x equals 2 we have the highest point, which happens to be 16. Alright, so what was the key here? Real quick, find critical numbers by using the derivative equal to 0 and using the derivative be undefined. Once you find the critical numbers, then you plug it into the original equation, and then you do the same thing for the endpoints, and then you compare, and that's using the comparison to determine which one is the lowest and which one is the highest. Wanna continue with the next one. We have let's find the extrema on the closed interval for the following functions. So let's start with A. First thing is first, check the two conditions. Is the function defined on a closed interval? The answer is yes. Is the function continuous? And that is yes, right? There is continuity here because this is never going to be undefined. Because you can plug in any negative number, you can plug in a 0, you can plug in a positive number. Alright, so those are continuous on this interval. And the next thing is to find the critical numbers. How do you find the critical numbers? By taking the derivative. That is going to be 2. That's going to be 2/3 times 3 x to the negative 1/3, right? By subtracting 1 from 2/3. Now that you have found the derivative, you have that's equal to 2 minus 2 over x to the 1/3. Then you're going to find the critical numbers. How do we find those? You have two ways to do that. First case is to set the derivative equal to 0. Second case is to set the derivative to be undefined. You set them to be 0, and then you solve for x. So you're going to add 2 over x to the 1/3 on both sides of the equation, and then you're going to do cross product, and that gives you 2 times x to the 1/3 equals to 2. Divide both sides by 2, and the 2's will cancel. Then you take the cube power on both sides of the equation, and that gives us x cubed, x to the x cube. No, sorry. The cube power of x to the 1/3 is x, and 1 to the 3rd is 1. So the next part is to find where this is undefined. What I'm going to do here is I'm gonna do that by setting it as one single fraction bar, and that's usually my strategy. This will make the process much easier. So try to write your derivative in one single fraction bar, and that is they have to have common denominator, and then put them in the same fraction bar. So I'll multiply this by x to the 1/3, x to the 1/3, and that gives me 2x to the 1/3 minus 2 all over x to the 1/3. This, and remember that this will be undefined whenever the denominator is undefined. So I'm going to set the denominator be undefined, and that tells me that that's going to happen whenever x is 0. That's the only way, right? By taking the third power on both sides of the equation, that will give me x, and 0 to the 3rd is still 0. So we have two critical numbers, and what we're going to do next is going to be we're going to compare them. Let's see, let me finish this one right here. So we're going to plug in f of 1, f of 0, and the endpoints are in this example -1 and 3. So plug into the original equation, and on the original equation we get let me write it out here. F of x is equal to 2x is at minus 3 x to the 2/3. So you plug in a 1 there, this will give you 2, and this will give you -3, which gives you -1. Plug in 0 there, this will give you 0, minus 0 gives you 0. Plug in -1 here, this will give you -2, this will give you positive 1, and then times -3 will give you -5, and then this will give you, when you plug in 3, this will give you 6, this will give you -3 times 9 to the 1/3, and we can see here that this number will be, I'll have to use the calculator for that one, just because it's going to be a decimal. So that would be 6 minus 3 to the power, no, sorry, times 9. Okay, I got, oh, sorry, let me, there you go. I got negative 0.24. So we clearly see that the minimum value of this function is, this is the lowest, and oh no, sorry, that's not lowest, actually this is the lowest. So, and this is the highest, right? Because the other numbers are negative. So that would be the highest. Yeah, so that will be the highest point. So the relative max is 0 at x equals 0. Relative min is -5 at x equals -1. Alright. What about the next one? So in the next one we have 2 sine x minus cosine 2x on this closed interval 0 to 2 pi. Now f of x is continuous. It's continuous because we know that sine is continuous and cosine is continuous, and the difference between two continuous functions is a continuous function. So we have here that this is a continuous function. Now it is a closed interval, so I want to be sure here and write it out. Be careful here with this. This is closed interval. All right, it's a closed interval, and so what we're going to do is find the critical numbers by taking the derivative of this. That is the derivative of 2 sine of x. It will be 2 times the derivative sine, which is cosine, minus the derivative of cosine 2x. We have to use chain rule here. So the derivative of cosine is negative sine. Leave the inside as it is, 2x, and then multiply by the derivative of the inside, which is the derivative of 2x is 2. Multiply those together, and that gives you positive, and move the 2 to the front, and that gives us this derivative, 2 cosine x plus 2 times sine of 2x. To find the critical numbers, again, we have to do both cases. The derivative is equal to 0 or the derivative is undefined. Let's think about this one first. Can the derivative ever be undefined for this case? Well, we know that cosine is continuous. We know that 2 sine 2x is also continuous everywhere. So we know that 2 continuous functions everywhere is also continuous function everywhere. So this is defined everywhere, so it's never going to be undefined. So now the next part is to find whenever x is whenever f prime is 0. So we're gonna set that equal to 0, and we're gonna solve for x. Now in this example here, we're gonna do one of those trig identities. We're gonna take sine 2x, and we're gonna separate it into 2 sine x cosine of x. The reason for that is because we can now solve the equation by factoring the cosines. You notice they both have a cosine as a factor, so we're gonna factor it out, and we're left. We're also gonna factor a 2 out, so we're left with a 1 from here, and we're gonna factor a 2 from here, so that leaves a 2 there. And we're gonna factor a cosine, so we're left with a sign there, and that gives us this product. Now, why do we factor it? Because remember, the zero factor property allows us to separate these two factors equal to 0, right? Cosine of x is equal to 0, or this is equal to 0, and that will give us two possible solutions. And then, so we're going to do cosine of x equals 0 whenever you have pi over 2 or 3 pi over 2. For this one, we're going to subtract 1 on both sides and then divide by 2, and that gives sine of x equals negative 1/2. And that happens between 7 pi over 6 and pi over 6. So what we're going to do now is we're going to check those points. So the function f of x is going to be 2 sine of x minus cosine of 2x. And then this point, you can use a calculator and to be able to compute these numbers, right? So let's try first the pi over 2. We're going to put 3 pi over 2, 7 pi over 2, and then f of 11 pi over 2. Oh, sorry, that's a 6. It's supposed to be a 6, and that's supposed to be a 6. All right, and then this is the critical numbers. These are the critical numbers. And then we're gonna do the endpoints. And the endpoints were 0 to 2 pi. So we're gonna plug in 0, and we're gonna apply in 2 pi. All right. So let's see. We can try this in our head. So we can do pi over 2 sine of pi over 2. That's just going to be 1. So that's going to be 2 times 1 is 2. And then here you have pi over 2. That will give you pi. Cosine is negative 1. So that gives you that. And so this gives you 2 minus negative 1. That is 3. Next one, we have sine of 3 pi over 2. And that's going to be negative 1. Minus, and then 3 pi over 2 times 2. That will give you 3 pi. And that will give you full rotation and a half, so that will be negative 1. And so this will be negative 2 minus negative 1 will be negative 2 plus 1 will be negative 1. Next one is 7 pi over 6. 7 pi over 6, that would be just a pi over 6 after the pi over 6 after the pi. For sine, that will be 2 times that will be a negative negative 1/2. Minus the cosine of that will be 7 pi over 3, which will be 1/3. Let me write it so I can visualize it. So this will be cosine of 7 pi over 3, right? Because the 2 and the 6 will simplify to be a 3. Let me write it out for you guys. So there's a 2 in front, and that will simplify to be 7 pi over 3. All right, so that would be a full rotation of 2 pi, and then plus 1/3. So the cosine of 1/3, that will be almost that's actually going to be 1/2. That's going to be 1/2. So then we're going to have here that's going to be 1/2. So then we have negative 2 over 2 minus 1/2 will be negative 3 over 2. Alright, so that's that one. The other one is 11. So we have 2 times 11 sine of 11 pi over 6, that's almost the 2 pi, so it's going to be negative. It's going to be negative, and it's going to be short, so it'll be negative 1/2. And then this is going to be cosine of 11 pi over 3. So that means it's going to be almost it's almost 12 pi. So would that be almost 12 pi? So we're gonna have let's see, 4 pi. So let's see, I always make how many times does it fit in 12 pi? 12 that will be 4 pi, and that will be 4 pi will be 2 rotations. So there's almost 2 rotations, but we are short by a pi over 3, so that will be positive 1/2. That'll be positive 1/2. Yeah. So that'll be negative 3/2. All right, for this one, you're going to have sine of 0 is 0, and minus cosine of 2 of 0, that will be 1, so negative 1. And then cosine of 2 pi will be the same thing, 0 minus 1 will be negative 1. All right, so we see here that the lowest point, the highest point will be 3, and the lowest point of the function will be negative 3/2. So we see here, because that's negative 3/2 is more than is lower than negative 1. So here we have relative max relative max is 3 at pi over 2, and relative min is negative 3/2 at either x equals 7 pi over 6 or x equals 11 pi over 6. Okay. All right, so I hope that this is helpful. We do have to be sharp with our trig functions, so hope you guys find this helpful. I'll see you guys next time.